Welcome to our discussion on perimeter and area of circles and polygons. So in this video, we're going to look at some properties of polygons, apply the concepts of similar triangles, and then apply the concepts of perimeter and area, basically by taking polygons and breaking them up into similar shapes. It really all boils down to whatever the polygon looks like. If you can break it up into rectangles and triangles, you can find the area of those shapes very easily. And then, of course, you add them all together and you can find the total area of just about any polygon out there. Okay, so we're going to begin the discussion with a very brief review of what it means to be talking about plane geometry. And that is, we're referring to objects like polygons, triangles, and circles, which have measurements like perimeter and area, and they're living, in a two-dimensional world. That's what plane geometry is. That plane is a two-dimensional world. But these ideas are quite useful in everyday life, our three-dimensional world, because a lot of our three-dimensional world is two dimensions, right? If you want to find the surface area of your room, right, you want to find that's 2 dimensions, right? If you want to find the surface area of the walls, because you need to know how much paint you got to buy, those are all 2 dimensions, right? So even though we live in a three-dimensional world, study of two-dimensional plane is very useful. So let's remind ourselves of some definitions so that we all know what we're talking about, right? A circle is your typical round object. The line that goes from the center out to any point on the edge is called the radius, and then the line that crosses from edge to edge through the center point is called the diameter, and thus the diameter is always 2 times the length of the radius. Polygons just refers to any straight-sided shape that has 3 or more sides, because 3 is a minimum. You can kind of visualize it. If you take the third side away from a triangle, there's no way to connect those 2 dots without another side, right? So polygons, poly meaning many, just means multi-sided objects. And of course, all the ones that we're familiar with, squares and rectangles, those are versions of polygons. They're just special polygons, okay? Anytime, any place where 2 sides come together, so all these little black dots, those are called a vertex. And then any time you connect 2 non-consecutive dots, so if we connected this dot down to this dot, that would be considered a diagonal of a polygon. It doesn't have to go all the way across, right? We always think of diagonals usually in squares and rectangles of connecting opposite corners. Well, the reason why is because if you only have 4 dots and you can't connect an adjacent one, right? The only option is to go straight across to the opposite one. But don't get into the mindset of thinking that has to be the case. Once you get more than 4 sides, a diagonal is just any 2 non-consecutive lines. And you can see you can have multiple diagonals coming out of one vertex. So, convex polygons is just a polygon in which all of the interior angles measure less than 180 degrees. So you don't have any obtuse angles. Remember we talked about acute and obtuse, and then we also have things that are bigger than 180, which it's not an obtuse, it's just bigger than 180, right? So you just don't have, basically, convex just means you don't have any Pac-Man shapes. So if you have a polygon that is all closed up, right? It's kind of like well, they're all closed shapes. Let me give you an example. So here's a polygon. Terrible drawing. This one is not considered convex because you've got like this concave area, right? This little cave area where somebody could go and hide. And the idea is that because we're always measuring the interior angles of our polygons, if you measure this angle around here where these 2 lines are, you can see very quickly that that's more than 180 degrees. So as soon as you get an interior angle that's more than 180 degrees, basically what you get is you get a non-convex polygon, sometimes referred to as concave polygons. And it's as if you took your finger and just pushed on a vertex and moved it inward and gave it a dent, right? So if it has a dent, it's been dented inwards, then these lines are now gone. Then that becomes a non-convex polygon, like I said, often called a concave. And here are the concave examples, right? So all it is it's just, like I said, you've got like a little dent. Something to notice when you have convex polygons, sorry, I went one slide too many, all of the diagonals are always inside the polygon. However, when you have concave ones, you could have diagonals outside the polygon. Very obviously, if we connect this dot to this dot, right? Because remember, it just has to be non-consecutive, so we can't go to a consecutive, we got to go to another one. But we could also connect this one down to that one, and depending on the shape, you know, I can't tell if it's to this side of that line or not. Probably is. But you get the idea. They could be inside, they could be outside. Okay, the interior angle sum of any polygon is based on the number of sides. So if you have 3 sides, you can only create one triangle out of it, duh, right? Because any 3 sides just creates a triangle. And we already know that the sum of the measure of the angles inside a triangle is 180. Any 4-sided object can be broken up into 2 triangles, and therefore the sum of the measures of the interior angles is 360 because you get 180 for the one triangle and 180 for the other triangle. And of course, if you think about some of our more common 4-sided objects like a rectangle or a square, you know that it's very easy to cut it in half, and there's one triangle and there's another triangle. And that's also how we've discovered, or are able to prove so easily, that a triangle is 1/2 base times height, because we know the area of this rectangle, if this is base and this is height, right? Height, that's h, height and h. Then we do base times height, and that gives us the area of the rectangle. But if we cut the diagonal, we now know this is half the area. And so we just take 1/2 base times height, and that's where we get the formula for area of a triangle. And of course, it works for triangles that aren't right triangles, but we can visualize it here with a nice little rectangle. And then if we expand this pattern, right? So we go to 5 sides, which now gives us 3 triangles. See, every time we add a side, we add another triangle, which means every time we add another side, we add another 180 degrees. So we start with 3 sides is 1, 4 is 2, 5 is 3, 6 is 4, 7 is 5, and da-da-da. This pattern goes on and on forever. So now you can see that you can generalize it, and the sum of the interior angles of a polygon always equals number of sides minus 2 times 180. So if you have a 10-sided polygon, you do 10 minus 2 is 8. You do 8 times 180, and that will tell you the sum of the interior angles. Next, using that information, let's see if you can find the sum of the measures of the interior angles of an octagon. First, you got to remember what an octagon is, right? How many sides it has. Octa, like octopus, which has 8 legs. So our octagon has 8 sides. So go ahead and pause the video and see if you can figure out the sum of the measures of the interior angles of an octagon. Did you get the right answer? Yay! All right, let's move on. Similar triangles. So 2 triangles are considered similar if the corresponding angles are congruent, and then the ratio of the lengths of the corresponding sides are equal. And really, as soon as the corresponding angles are congruent, it forces the ratio of the lengths of the corresponding sides to be equal. And ergo, if you go in the other direction and you force the lengths of the corresponding sides, the ratio of the lengths to be equal, that will force the angles to match up. So it's basically, you only need one or the other, and it forces the other half. Here's a very typical similar triangle problem that you'll see in books. Suppose a man who is 6 feet tall is standing 20 feet from the base of a tree. The sun shines on the tree and the man, obviously, right? And casts a 30-foot shadow as seen in the figure. How tall is the tree? Well, we know that the shadow length of the tree and the height of the tree, along with the angle that the sun comes down, which we can figure out because you basically just draw a straight line from the top of the tree down to the end of the shadow, that creates a triangle. Well, because the sun is coming down at the same angle for everything, then from the top of the guy's head down to the end of his shadow will be a similar triangle, right? It'll have the exact same shape because it's using the same angle of inclination, right? The same angle above the horizon. So they share this angle here. They both have the right angle because we're talking about the height of the person versus their shadow. So that creates the right angle. So because they share this one, they both have a right one, then we know the angle at the top is identical. And once we have that, we know that the ratios of the sides are the same. And what I mean by the ratio of the sides is if you take the height of the tree and divide by the length of its shadow, it's going to be the exact same ratio as the height of the man divided by the length of his shadow. And of course, we could do all of these ratios. We could do the shadow over the height would be the shadow over the height. We could do the hypotenuse of the big triangle over the height is the same thing as the hypotenuse of the smaller one over the height, and so on and so forth. It's just obvious if we're trying to solve for the height of the tree, we want to use that as part of our ratio because we want to solve for it. And then we also want to use things that we can measure. We can't really measure this invisible, sun ray that's coming down, but we can measure our shadow. So it makes sense to set up your ratio as the height of the tree over the shadow of the tree is going to be the exact same ratio as the height of the man over the shadow length of the man. And that's what we do. There's the unknown height of the tree over its 30-foot shadow. There's the height of the man over its 10-foot shadow. Do some very simple math of multiplying both sides by 30 to get rid of your fraction, right? And so that you now know that x, when these cancel, x is just going to be 30 times 6 divided by 10, which gives you 18 feet. And we know the tree is 18 feet tall. So like I said, very common, easy way of figuring out height. And in fact, it's how surveyors can figure out heights. They don't need similar triangles. So a surveyor can sit at a certain point and then shoot a laser basically to the top of an object. And their instrument will tell them what this angle is. Then they also know their distance to the object. And based on that, they use trigonometry to figure out the height of the object. It's pretty cool. Okay, the perimeter P of a polygon is the sum of the lengths of the sides of the polygon. Well, that should be, pretty straightforward. So it doesn't matter how many sides it has. It doesn't matter if it's concave or convex. The perimeter is always just add up all the sides. Here's some typical polygon looking things, right? You would just add up the lengths of all of the sides if we're on this nice little, unit hex board, graph paper kind of stuff. And you know how long each line segment is. You can just add them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of them. So we know its perimeter is 12 units. And then whatever this unit is, you could multiply by that. Like so if this is a quarter inch, you would do 12 times a quarter of an inch, and you get 3 inches total, that kind of thing. Maybe it's 1 centimeter, then you get 12 centimeters, whatever it happens to be. Same thing here, right? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 total units for that one. Now this one's a little trickier because we got 1, 2, 3, but then how do we do this one? Well, we got to use the Pythagorean theorem. And we got to remember the Pythagorean theorem is the square of the side plus the square of the other side equals the square of the hypotenuse. Well, we see this is a length of 1, length of 2, so we square each of those, get 1 and 4, we add them together, so c squared equals 5. Take the square root of both sides, and c equals, technically, algebraically, right? If this didn't have a picture, if we were just doing this math, c would equal plus and minus negative 5. Because remember, if you square a negative, it becomes positive. But because we're working with a shape and we're working with distances, you can't have a negative distance. So we throw away that negative square root of 5, and we just say, it's got to be a distance of square root of 5. So the perimeter of this thing would be 5, right? The 1 plus not the 5. The 1 plus 2, which is 3. 3 plus the square root of 5. Okay, the area of a polygon is just defined as the number of square units inside the polygon. And simple ones are easy. A rectangle, the perimeter is really easy. It's 2 lengths plus 2w, right? And then the area is length times width, or what I said earlier, base times height. And the reason why I use base and height instead of length and width, it helps you generalize to when we start looking at volumes and finding volumes of things. And it also helps you generalize to other shapes. So I just like base and height. A square, we know the perimeter is just 4 s's all the way around because they're the same. And then, of course, area is base times height when they're both s's, so you get s squared. Triangle, we've already talked about this, where we've got the base of the triangle and the height of the triangle. See, we're already saying base and height. And if we were thinking about the other ones, then you could see the correlation between what those words mean. But in any case, we know it's 1/2 base times height. And I showed you that lovely little picture of it being inside of a rectangle to kind of convince you that that is true. Parallelogram, of course, you can just sum up all the sides. You just got to know what they are, right? And if they tell you certain things, then you can always solve for them. And then the area of a parallelogram, surprisingly enough, is just easily base times height. But you can see why, because if you take one of the triangles on kind of the concave side and cut it off and move it to the other side, right? So you take this triangle here, and you cut it off. Take some scissors and cut vertically right down here, and then move this over here. You can see that it's going to fit perfectly right there. And now you have a perfect rectangle, right? This shape right here is a rectangle, and we know that rectangle is this height times this base. And remember, since it's a parallelogram, this full base over here is the same thing as this base there. So you get base times height. Trapezoid. Trapezoids are a little different, right? But again, you can visualize it. Okay, cut this one off. And put it over here. Now you have a rectangle that is this shape here. Right? Well, you need to figure out what this length is. Going from here all the way out to there is what length? Well, it's not, if you take this down, don't think of it as being all of base 2. It isn't, right? Because if you see visually, this black line is really the same as this piece right here, and base 2 has this little extra bit here. So how do we figure out, what they are? Well, you can do a bunch of math and you can geometrically figure it out, but I'm not going to bore you with it here. Basically what happens is it's the average of the small and the big side, right? So if you take base 1 plus base 2, add them together, divide by 2, that's giving you the average of those two lengths. You take that base times height, and again, base times height, base times height, base times height, right? We get in the area of that shape. Well, now we can take this idea and we can apply it to all sorts of other shapes. All you got to do is break them up into rectangles. So now we know this one down here is simply 9 times 40, and then this one up here, right, is 7 times, well, we don't know this distance, but we know this is 28 and this is 40. So we do 40 minus 28, we get 12, 7 times 12. And you would add those two together, and that's the area. Here we go. And you could do it a different way, right? So the author decided to cut it vertically instead of horizontally, get their first rectangle of 7 plus 9 is 16, and then there's the 12 that we got from 40 minus 28, and then this leftover piece is 28 by 9. So there's always going to be more than one way to tackle it. You're always going to get the same answer, just as long as you go slow and you don't make any silly mistakes. You put everything together, you get the total area, and then the question was, they need to know how much paint, right? So they're painting this floor. Well, we know a gallon of paint will cover 300 square feet. Well, we don't know that. It actually varies from different types of paints. But let's say the paint you're buying covers 350 square feet. So you take your total of 144, divide by 350, and you get 1.27. So you need a little bit more than 1 gallon, which, one and a little bit more than a quarter of a gallon. So you could, if you wanted to, get a gallon and a quart, I think, is a quarter, so a little bit more than that. So maybe a gallon and 2 quarts, but it's probably going to be cheaper just to buy 2 gallons. I have a bunch of leftovers, which is always good anyways, because, the dog's going to scratch it with its nails and the kids are going to drop things on it. You're going to have to touch it up eventually. All right, why don't we try this skill check? Go ahead and pause the video, give it a read, see if you can draw yourself a picture, right? Always draw a picture with these things, label everything, solve for any of the missing pieces, and then see if you can get the correct answer. Did you get it? All right. On to the next one. Let's find the area of this parallelogram. Well, we already know the formula. It's just base times height. Can't get any simpler. 78. Okay? Area of the triangle. Again, we know it's really easy. It's 1/2 base times height. So 31 times 6, right? Because you can take the half of either one. If you take half of 31, it becomes a decimal, and that's just, a pain in the butt. But if you throw it all in your calculator, 0.5 times 31 times 12, enter. It's going to do it for you anyway. There you go, 186. Area of a trapezoid. Well, we just figured out, remember we figured out trapezoid is you have to do the average of the two bases. So this base plus this base divided by 2 times the height. So there we go. Plug everything in and get 130.5 square feet. Next, we can start talking about circles. The circumference of a circle is the area around the circle, right? And we can no longer add up sides because a circle doesn't have sides. It's got one big curved surface. And the Greeks were nice enough to figure this out hundreds and hundreds and hundreds of years ago, that the circumference is simply 2 pi r, or pi times diameter. I like 2 pi r. And the reason why I like 2 pi r is there's a strong correlation, there's a strong relationship between circumference and area, because area is pi r squared. So area equals pi r squared. Now, you probably haven't had calculus, but once you take calculus and you learn how to take a derivative, if you take the derivative of this, right, so the derivative of area with respect to your radius is simply 2 pi r, because the rule is the power comes down and then the power goes -1. 2 minus 1 is 1. And look at that. That is circumference. So the circumference of a circle is literally the derivative of the area. Now you're probably thinking, I have no idea what those words mean, but when you take calculus later, you'll remember back to this and go, oh yeah, I remember that. So that's why I like the 2 pi r instead of the 2 pi, instead of the pi times diameter. But of course, since 2r is equal to diameter, you could always use that. But in any case, here's how we can calculate area very simply by just plugging in for our r, and here's how we can calculate circumference. Just remember that you do order of operations correctly, right? You square it first, then you multiply it by pi, and then you're done. Now, see if you can figure these ones out. Find the area and circumference of a circle with a diameter of 10 inches. Draw yourself a quick little picture. Make sure you label the diameter as 10 and not the radius, and then you should get the correct answers. Did you get them? Good. Okay, another example. Consider the size of the lawn at a local park. The park consists of a grassy rectangular area determined by the dimensions of 228 feet by 380 feet. And there's our little picture. Now, we need to install circular sprinklers in the park in order to cover the grassy areas for the most complete coverage of the park grounds. A sprinkler has a maximum radius of 38 feet, and the sprinklers will be placed in a grid-like pattern as seen in the picture down below. If we have 15 sprinklers, how much of the grass will not get water? So basically what they're saying is calculate all the green bits, right, that aren't covered by the sprinklers. And this is actually a really big problem trying to water rectangular areas with round sprinklers, which is why you may have noticed if you've ever flown across the middle of the country, you will see farmland below you and their crops are planted in circles. And you're like, well, why the hell are they planting their crops in circles instead of rectangles? And it's because they can maximize their yield because they can put a sprinkler in the middle and get the whole crop irrigated. If they planted it into a rectangle, all the stuff out here would die because it wouldn't be getting enough water. Okay, so if you weren't given that picture, when you have these types of word problems that involve geometric shapes, as I've said before, the first thing you always want to do is draw yourself a picture. We're visual creatures, and we can kind of understand what's going on if we can see a picture. So we draw that picture. You don't have to be fancy, right, and use colors and put in all the little fancy little things here, but just give yourself a rectangle, throw in some circles, and go, okay, I get it. I'm looking for the difference between the areas of these things. Right? I can find the area of each circle. I can find the area of the rectangle. I can multiply the area of the circle times how many I have, right? Which is 15 of them. And then I can basically just do the difference between those areas. That's all I have to do. And once you've drawn that picture, you can figure that out. So first thing we can do, find the area of the rectangle nice and easily. 228 times 380, get this area. Then they tell us we have 15 sprinklers, and each sprinkler makes a circular pattern with a radius of 38 feet. So there's our radius. So of course now we can find the area of a sprinkler, right? The area covered of a sprinkler. And we square, multiply by pi, and get this approximate answer. Then there's 15 of them. So we take that, multiply it by 15, and we finally have, after a couple steps, the full coverage of our sprinklers. And then we subtract that, right, from the full amount of the park, and we can see that quite a lot, right? 18,000 square feet is not getting watered. And if you take that 18,000 and divide it by 86,000, you find out that's 21.5% of the grass is not getting watered. That's going to be a lot of dead grass that you're going to have to pay for. So you better figure out a better way to irrigate this stuff. All right, that's the last one I got for you.